So on to our third talk today. There's a slight change in tack here. So our third speaker is Thomas Sabat. He's Chief Operating Officer of Vaticle, previously known as Graken. So at Vaticle, he works closely with Vaticle's open source and enterprise users who use Graken to build applications in a wide number of industries, including financial services, life sciences, cybersecurity, and supply chain management. A graduate of the University of Cambridge, Thomas has spent the last 7 years founding and building businesses in the technology industry. So today, Thomas will discuss enabling the computational biology of the future. And I'll just hand over sharing to you, Thomas.
Is it sharing now?
Not yet.
How's this? Can you see the screen?
Yes, we can now.
The slide?
Yes.
Okay, good. Well, thank you very much, Mark, for that very kind introduction. And Nicola, I was very happy to see the last screenshot. That was a screenshot of TypeDB. Since we've been very fortunate to have one of your colleagues, Henning, I think, presented several of our conferences. So I think this talk, at least, is, I think, a very good follow-on from Nicola's talk. He focused mainly on the text mining aspect. And what we build is really the infrastructure to store the data. As effectively, we build the database software. And in this talk, I want to really summarize or share the story of how we've learned, the learnings that we've had from working with a lot of different biotech and pharmaceutical companies over the past couple of years. Mark already mentioned it. TypeDB is used for many different industries. Really, any industry that works with complex data uses our software. But we've seen particular uptake in the life sciences because there is so much complex data, and because there are so many ontologies that describe effectively the same data, and we need a data model that is flexible and expressive enough for us to actually handle that data, both in terms of modeling in a way that's easy but expressive enough, and also a simple and easy way to query for data. But as the title of my talk suggests, I want to be talking about the future of biology, because it's something that personally interests me a lot, and I'm always very humbled by some of the projects that we are invited to participate, at least our technology. And so before diving into specifics, because we will be looking at quite a bit of code, so this will be a fairly technical talk, hopefully interesting and to inspire you on how to potentially use TypeDB to build knowledge graphs, but especially in the context of how we can enable the computational future, because we've seen quite a lot, especially in the exciting, innovative stuff. And so when we look into the future, and that's kind of where we want to start today, when we look into the future, specifically starting with 2025, there's a couple of key innovations that I want to focus on, at least to start. That certainly that whet my appetite for the future, and that's the potential of having 360-degree real-time patient views. We also have the rise of hyper-personalized medicine in terms of being able to actually get diagnostics and therapeutics that are personalized to our own genomic and biological profile, but also the ability to do in silico clinical trials, and something that we've been speaking a lot about today, which is de novo drug design. And a lot of these topics, I think, especially if you're let's say a normal person that isn't really in the biotech space, a lot of these are very abstract and I think very exciting ideas that feel very much in the future. But I think that what's particularly encouraging is that a lot of it is already happening. For example, earlier this year, I was excited by AstraZeneca announcing that they found the first drug candidate that was going into their pipeline from their partnership with Benevolent AI. And a company that we know very well, Peptone, a startup here in Europe is doing some fantastic thing with an incredible pipeline that they've built to do protein engineering. But something that is clear, and that's where we are involved in a lot, is the fact that the future of biology is computational. And this seems something almost, especially from our point of view, almost self-evident. And we see studies coming out, for example, here a couple of years ago, showing that 90% of principal investigators saying that they will or will soon be working with large data sets. And then when we look at some of the companies in this space, especially some of the more innovative one, if we look at a company like Recursion Therapeutics, they generate 65 terabytes of data every single week. So the bottom line is that there's a lot of data. And because of that, we've really, as an industry, gone from asking ourselves, what is computational biology, to really asking, is there any area of biology that doesn't involve computation? Now, of course, despite all the exciting stuff that is happening and the innovative technologies that are coming up, I think a graph many of us are familiar with is that the return on investment of drug discovery investments has been dwindling certainly over the last decade. But the technologies and the innovations that have come out are there to really change fundamentally how we do biology. And I find this extremely exciting. But in order to do that, one of the fundamental things we have to consider is, how do we manage data? We have a lot of data, but big data isn't the whole story. We also deal with the fact that we have complex data, and we'll be speaking about that today as well. But first, let's actually be practical and think and establish what type of data are we really talking about. So the first type of data that we see a lot when we see our software being used is internal and legacy data sources. So especially in larger pharmaceuticals, there may be databases sitting across the organization in SQL and Oracle databases, and perhaps more modern MongoDB databases, all of which aren't actually connected with each other, may have different data models. And there's also publicly available data, whether it's Ensemble, CTD, Reactome, Ensemble. All of these data is effectively describes similar concepts, but also uses slightly different or very different ontologies or data sets. And of course, as we saw in the previous talk, I think brilliantly described, is we've got a vast number of medical text data that we actually also need to compute over. But first, let's look at actually how that data looks like. If we have it in a structured format, so let's say we have done the difficult part of, especially on the unstructured text, creating some sort of structured representation that we can compute over it. How does that data really look like? And let's say we've got a disease that we connect with a drug. If that's the end game of at least in drug discovery, there's a lot of variables that we have to consider. There's genes, phenotypes, pathways, compounds, kinases. The fact of the matter is that this type of data is very, very complex, and current databases in particularly really struggle to handle this type of complexity. And the result that we get if we use something like SQL is that in order to ask simple questions, we end up with SQL queries that may look like this. And this is actually an article that we published after one of our users showed us how they could do this. And the key issue is that it's very hard to model and integrate heterogeneous data sets. And the key part here is the heterogeneity, if I'm pronouncing it correctly, of biomedical data. That's particularly notorious. But why is it that it's so difficult to model biomedical data? So first, how do we model data? What are the processes that we go through? Now, first, if we start with some model, if we are modeling some domain, let's say domain with drugs, proteins, and anything associated to it, we would probably start by choosing the major entities that we need to consider. So let's say, for sake of simplicity, we've got a protein that we want to connect to a drug. We then want to connect them through relationships. So we will identify the relationship types. Here, we want to identify an interaction relation between a protein and a drug. We want to determine which attributes belong to which entities. So in this case, let's say a protein has an attribute, UniProt ID, and a drug has an attribute, Campbell ID. And then, and this is possibly the more difficult step, is normalizing that data. And that normalization process, which I think one of the talks spoke about today here as well, is effectively trying to get our data in third normal form, which, especially if we're working in a relational database, can be either really, really difficult, really tedious, but it's going to take a long time. And the result, especially if you're working with data that at a conceptual level has a lot of different relations, there's a lot of different types of entities, you end up actually losing quite a lot of the semantics when you're normalizing that data to third normal form. So why would you use TypeDB? Why are so many people using the software, especially in the biomedical space, to actually model biomedical data? Now, the simple reason in the context of this slide is that you go through all these 3 steps, but we don't have to normalize the data. And I think we don't have to normalize the data simply because the conceptual model, which is the model that you make when you follow the first 3 steps, that is the model that you implement in the database. And that's something really, really important. Because the model that we've created here, this simple model with 2 entities, 2 attributes, 1 relation, effectively encode in TypeQL, which is the language that we use to model our data, to query for our data, is directly, effectively a representation of this concept level schema. And that's why we say that TypeDB implements a concept level schema. And at least for those unfamiliar with TypeDB, this schema is effectively is the representation of what we're trying to model. And yes, TypeDB implements schema constraints that enables you to effectively make sure that your data is safe. So nothing that goes in, so everything that goes into your database, you can be sure that it adheres to the schema to ensure type safety. But here, right now, we're defining a protein, which is saying the protein is a type of entity. The protein owns an attribute of type UniProt ID. It plays a role, the role of interacted in the interaction relation. And then we do the same for a drug that owns a Campbell ID attribute, but the drug plays the role of interacting in an interaction relation. Then we also declare the interaction is a relation. And finally, we also declare the types of the attributes themselves. And by the way, about 70% of the entire language, of the keywords at least, is on the right. And we've dedicated our lives to at least trying to make this language as elegant, as simple, yet as expressive as possible as we can, in order so that people like yourself or anyone working with complex data can have a language that is very simple and intuitive, that's not difficult to learn, but can represent very, very complex structures. So let's say we want to extend this model. Let's say we also, that because biology is complex, there's many types of proteins. Let's say for the sake of this example, there's 2 types of proteins. There's a kinase and there's an ion channel. And we want to represent what we would call here would be a type hierarchy. And we call this a type hierarchy because all kinases are proteins, but not all proteins are kinases. And to create that hierarchy, we would very, very simply use, again, the keyword sub, just like we would use the keyword sub in order to declare that a protein is an entity. And here we can simply say kinase subprotein, ion channel subprotein. And very importantly, you can add this to the schema at any point in time during the database's lifecycle. So it's not as if you have to predefine your schema completely before you start ingesting data. The point is that the schema changes and can change during the course of the database's lifecycle. Now let's look at how we can retrieve some data as well. Let's say we want to return kinases and ion channels that are connected to drugs. Effectively, in a sense, this query means that there's 2 relations between a kinase and an ion channel with a drug. So there's effectively 2 paths here. But this is where the type inheritance becomes very useful, because rather than actually having to write in the query, having to write 2 different query paths, we just write 1 because we can simply ask for, give me drugs connected to proteins. And by asking for proteins, TypeDB will infer effectively through the type inference, it will infer that protein means also kinases and ion channels. And there's a lot of different types of relations that we can model with TypeDB. One of the reasons many of our users use the software is because of the expressivity that can be modeled. Actually, I would at our last conference in April, Henning also spoke with one of Nicola's colleagues, and he had some great examples as well to present there. And some of those examples are things like ternary relations. And a ternary relation is effectively a relation that has 3 role players in it. Here, in this example, we've got an encoding relation between a gene and a protein, but we also have a source, and that source may be a database. That, of course, depends on how you decide to model it. But the key thing here is that we can model more than 2 things in one relation. And by the way, this is something very important, because what TypeDB does is that in the data model, entities, relations, and attributes are all first-class citizens in the data model. So if you want to effectively create even things like nested relations becomes possible. And a nested relation is effectively where I've got one relation referring to another one. And the example showing here is basically saying that if I've got a protein interaction between 2 proteins, I can now localize that protein interaction to a tissue or to another entity through another relation. And we do that by assigning effectively a variable, which is what that $sign is doing. $PPI is being assigned to that protein interaction relation, which we later use in the locates relation, where the $PPI plays the role of located in that locates relation. Another big component of TypeDB is the ability to infer new data, and that's where the inference engine comes into play. So the inference engine, the RU engine, effectively allows us to, for example, infer new gene to disease associations. So an example here would be where, let's say I defined the name of the rule, but let's say I want to say that if a gene encodes for a protein, and if that protein is associated to a disease, I want to infer that the gene should also be associated to that disease. I can create the conditions by stating those in this case, in the when statement of the rule, by creating these 2 relations, and I can then, in the then part of the rule, I can simply create the relation that we're inferring. That the example is wrong. I apologize here. They should have said gene disease. Then this gene to disease association will be created. So here now you're effectively inferring a new relation between a gene, in this case, and a protein and a disease that otherwise wouldn't be there. And that downstream you can use for whether it's your machine learning, whether it's whatever you want to do with it. When you query for it, the data will be there as if it actually existed there. Now, at some point, you may be asking yourself, why do these constructs matter? And I think that's a very fair question. Now, my first answer would be is that it makes your life so much easier. A slightly more serious answer would be is that we can finally model the real world as we perceive reality. And this is really, really important, because especially in the biology field, where a lot of the IP that you have sits in the way you understand the world, therefore effectively the data model, being able to represent that in a computer in order to compute over that is effectively IP that sits right there in the data model. Now, but how do we go about building that? And that's what the final part of this presentation will be about. So how do we build with TypeDB? First, what can we build? Now, that really depends up to you, and I'm no expert here, so this is really just relaying what some of the, I guess, geniuses that are using our technology have used it for. Things like disease understanding, data harmonization, precision medicine, competitive intelligence, expert systems, supply chain optimization, clinical trial cohort selection, and drug discovery. But there's many more use cases that we can use it for. And the questions that we then think of asking are questions like, which genes are located near to each other, where one gene encodes a protein that participates in a specific functional pathway? Or which compounds have the lowest number of adverse effects ranked by levels of evidence? Or what are the trials that the competition is running and for what compounds? Effectively, questions that touch a lot of different type of data and that may seemingly sound simple, but actually are very hard to compute over. Now, TypeDB never works alone. TypeDB is I would say, it's just a database. It needs an architecture to work. And the first step of that architecture is really deciding what data goes into your database. So if you've got public data sets, you've got legacy internal data, you've got medical text, if you've got a great NLP pipeline like the one Nicola described, you want to then push that into TypeDB, and you can do so by using connectors, for example. Whether it's something, whether you're streaming your data, whether you build your custom loaders, or you actually use an open source library, one that is actually very popular within our community, which is called TypeDB Loader, which actually was also open sourced by the Bayer team, something they developed, and they open sourced it, which is on GitHub if you want to use it. And it's a great tool to migrate a lot of big data into TypeDB. We can then use one of the client drivers that TypeDB offers. There's Python, Java, Node.js, and there's actually a bunch of others in the community that are being developed from Rust to Julia. But in order to migrate that medical text, we also want to use some sort of text mining tool, whether you use an open source tool like CoreNLP or OpenNLP, or you develop something yourself like Nicola showed us. Once we have it in the database, we can then, of course, expose it to applications, whether it's to create dashboards, analytics, chatbots, you name it, that really depends to you. So let's say we're loading data. That's usually where many people would start after they've created the schema. Now, a question we get a lot is, can we automatically map SQL, JSON, etc. to a TypeDB schema? The first answer, the short answer, is that we could, but we shouldn't. Because if the data is already normalized in third normal form, we're not really going to gain much from TypeDB's schema. And so that's why if we really want to get value from using TypeDB, we want to ask ourselves, given TypeDB's type system, what is the best model for my data? So if you have data in CSVs, if you have data in XML and JSON and SQL, whatever, you actually want to think, you want to think about your data model first. You want to think, how should I have modeled this if I was using the TypeDB model, which includes entities, relations, roles, attributes, and you want to spend considerable time thinking about the schema, because this is where you can generate huge amounts of intellectual property by the schema that TypeDB enables you to create. And to show what I mean, let's look at some tabular data. Let's say we have a gene table, a disease table. How could we think of mapping this to a TypeDB schema? Now, one way is just to think, what are the entities and relations in this example? And this is a very simple one, where here we would say, well, we've got two column names. Those should be attributes, symbol and ensemble ID. And I've got an entity, which is gene. So in this case, the entity refers to the whole table. And we may choose to do the same here as well, where the disease is effectively the table and the mesh ID and the name are the attributes. And the foreign keys that we see here refer to the relation. That would be a very simple way and effectively a very easy way of mapping it. Unfortunately, when you start to look at more complex data, it becomes slightly less obvious like that. And you may find some tables shouldn't actually be entities, and perhaps they should be relations. They should be attributes. That really is something that depends on the type of data that you have. Similarly with JSON, if we have some sort of JSON document like this, we would also start to think, okay, what are the entities that I can map, the type of person types. Here is the publication, what are the relations that may exist between them, because a lot of some of the semantic information in relation to the roles, to the relations, is not really captured in a document like this. So you have to use kind of your own interpretation, effectively your subject matter expertise, to really model this in the most appropriate way. And as a final point, I want to just look at just 3 examples of how we could actually implement this in practice. So let's look at competitive intelligence, drug discovery, and precision medicine. And for each one, we're going to answer a question. So for the first one, we're going to answer, who are individuals who own patents and have run clinical trials on Ebola? For the second, we're going to answer, what are the most likely gene targets for melanoma? And for the third, given someone's biological and genetic profile, what clinical trials is an individual eligible for? So let's look at the first one. Now let's say we're interested in finding those different patents and trials. We probably would want to start by thinking of what type of clinical trial data do I need? I'll probably need some patent data as well. And by the way, Lens is a great website to an open source data set that you can use. And then possibly some of the more usual annotated data suspects like ClinVar or Reactome or DisGeneT. You then want to push that into your database. You may want to do some NLP, and then with TypeDB's client drivers, push that into the database. And once you've done that, we can start to write queries to answer that question. Who are individuals who own patents and have run clinical trials on Ebola? Now, once we've modeled the data in this way, this query would effectively look like this, where we're first in the query itself. First, we use the keyword match to state that we are asking for data. We define the types of entities that we're looking for, specifying specifically that we want a disease that has the name Ebola. And then we just simply create the traversal, which is effectively a patent is connected to a person through an ownership relation. A person is connected to a trial through an investigation relation, and a trial is connected to a disease through an involvement relation. And the result is effective, and the result would be the persons that we want to be returned by, who are the owners of those patents. Now let's look for the next one. So drug discovery. What are the most likely gene targets for melanoma? Now, if we start first with data sets, probably if you're doing drug discovery, you need quite a lot of data, especially large amounts if you're touching a lot of different, especially annotated data sets. If you're pharmaceutical, you're likely want to perhaps use some of your legacy data sources as well, if you have those, of course. For medical text, you want to have some sort of core NLP, some sort of text mining to create the structured representation of that data. Finally, we create our schema and we push it into TypeDB. And this is where it gets interesting, because like I said, TypeDB never works alone. And because of the rich type system that TypeDB offers, there's a lot of semantic information in there. So there's incredible amounts of machine learning that we can do, that we can learn over the graph to predict, to make predictions. And actually KGCN is an open source project that you can also find on our repository on GitHub that is effectively that allows you to do convolutional neural nets from TypeDB concepts. And the way it works in rough terms is that we create a subgraph, which is effectively represented through a TypeQL query. That subgraph goes into the learner, and that subgraph makes predictions. And every time we run the learner, we would actually want to store those predictions back into the graph. We can version it. That really depends on how you want to do it. But the great thing is that once we do that, and perhaps we use other machine learning algorithms as well, is that we can use those as evidence to effectively output a list of targets that are the most likely gene targets for melanoma. And then if we have modeled in a certain way, we can ask the question that, given some sort of score that we've generated, that we can just simply output a list of gene targets that are of interest. And this is actually taken from a project that is being done right now by a pharmaceutical that is implementing not just one of those machine learning algorithms, but a bunch of those, and then use them as evidence to effectively find hypotheses, to find new targets in conjunction with actually also the reasoning engine, which is what I'll be showing in the last part here. And here, given someone's biological and genetic profile, what clinical trials is someone eligible for? Now, precision medicine is really great, and I think it was only a few years ago that this particular data set was made available at clinicaltrials.gov. Sorry, actually, I meant this one, which is a great precision oncology knowledge base that is available to use, which is particularly interesting if you're doing precision medicine and looking for at least open source data sets. But we would be thinking about a similar type of structure. We want to get our data into TypeDB, and then being able to ask a question like, given someone's biological and genetic profile, what clinical trials are they eligible for? So, and this one is interesting, and if you may have questions at the end, which please do if you have, because the key here is that this relation effectively is asking, this query is asking, give me a trial that's connected through a personalized therapy relation tied to a person. But the interesting thing here is that this relation, this personalized therapy relation, is actually inferred. It doesn't actually exist in the database. And the way we've inferred that is by having two hypotheses. First, we infer the relevance for a clinical trial. That means that a patient has the same gene and variants mentioned in the trial, and they are eligible as well for the clinical trial. So what we do is effectively that we infer that relation based on first infer a relevant trial relation, and also we infer an eligible trial relation. But then those two relations themselves are also inferred, because firstly, that inference is made by this rule, which is effectively a quite simple rule. But then the relevance, this relation right here, is actually based on the fact that someone has to have the same association, the same variant. They have to have, and they have to have the same gene. And the trial, in this case, we keep it simple here, but we could say the trial must mention both the gene and the variant, and we can then quite easily effectively represent that in a rule which could look like this. Now, because of time, we won't go into detail here. And we do a similar thing here for eligibility. We can create the right conditions that if the trial is associated to the disease that is associated to the person, and then we find effectively the personal information like the age and the gender needs to be relevant to the trial as well, which we can also represent as a rule. So the point here is that we can be quite generic, quite specific in the conditions that we're making in the inferencing to effectively infer new types of information. And the result is that we can answer the question, given someone's biological and genetic profile, what trials is someone eligible for? So in summary, and I've only got a few slides left, there's a lot we can do with TypeDB. This was really just a way of summarizing some of the great work that other companies have done with our technology. Keep in mind all the different things that TypeDB doesn't work alone, and there's a lot of connectors and different drivers that you can use to effectively make the best out of TypeDB. And as a closing note, I think there's a lot of exciting stuff happening. And if you want to get started, there is an open source repository that I would encourage you to check out, which is this BioGrac and COVID. I think we are renaming the name, but this is open source. If you want to look at an implementation of TypeDB and look at some open source schema, this is where you can start. And I would end by saying, start building. Everything that I showed is open source, by the way. So if you are interested, join our Discord community. I'm on there every hour of the day except for when I'm sleeping. But do hit me up if you have any questions, and I look forward to your questions.